In this video, we're going to bring together all the concepts that we've learned throughout this playlist by doing some review problems. So starting with our first example, we have the unit circle here, and we want to first find tan of 90 take theta degrees in terms of P and Q. So let's rewrite this. We have tan of 90 degrees take theta. And trying to visualize 90 take theta degrees on the unit circle is going to be quite difficult. And so we're going to avoid trying to solve this problem by doing any sort of visualization or geometry on the unit circle. But what we can do is realize that we have a difference of two angles. And so the angle difference identity will come in handy. And so because we got tan, let's try the angle difference identity for tan, where we're going to have tan of 90 take theta will be tan of our first angle, tan of 90. And because we have a take here, it's going to be subtract tan of our second angle, tan of theta. And we're going to be dividing by 1. And because we have a take here, it's going to be the opposite, plus tan of our first angle, tan of 90, times tan of our second angle, tan of theta. Now the next step will usually be to sub in our exact values, but realize that we've got tan of 90 degrees, which is undefined. And remember, it's undefined because 90 degrees is on the positive y-axis, and this is parallel to the x equals 1 line, and therefore there will never be an intersection point to represent a tan value. So it turns out that we cannot solve this problem using the angle difference identity for tan. And what we have to do instead is use the fact that tan of 90 degrees take theta is going to be equal to sine of 90 take theta divided by cosine of 90 degrees take theta, where we're going to avoid the situation of trying to find the exact value for tan of 90 degrees. And I should say that it's always good practice, in my opinion, to solve angle sum and difference problems with tan in this way here, as you avoid the case where you have to find the exact value of tan of 90 degrees. And you may also find that on most formula sheets, the angle sum and difference formula for tangent will not be there because it's not as general as you think. So let's continue our problem. We can expand the right-hand side by using our angle difference identities for both sine and cosine. So starting with the top of our fraction, we can use the angle difference identity for sine. So this will be sine of our first angle, sine of 90, times cos of our second angle, cos of theta, subtract cos of our first angle, cos of 90, times sine of our second angle, sine of theta. And we're dividing by cos of 90 take theta, which we can use the angle difference identity for cosine. So this will be cos of our first angle, cos of 90, times cos of theta. And because we got to subtract, we did the opposite. It would be plus sine of 90 times sine of theta. And now we can use our exact values to make some simplifications. So we know that sine of 90 hopefully is 1. And cos of 90 is 0. And we have another cos of 90 here, which is 0, and sine of 90, which is 1. And so by making these substitutions, we get 1 times cos, take 0 times sine, which is 0, and we divide by 0 times cos, which is 0, plus 1 times sine theta, which is sine theta. And now by representing this result in terms of P and Q, we know that cosine of theta will always be the x component read off the unit circle. So this will be P, and we divide by sine of our angle, and sine of our angle will be the y component, which is Q. And so you can see here that our result for tan of 90 take theta is actually just P over Q, or cosine over sine. And just as a little extension, we know that tan is equal to sine over cosine, and because we got tan of 90 take theta is equal to cosine over sine, this is actually just the result of 1 over tan of theta. And so in fact, it might be an interesting result for you that tan of 90 take theta is actually the same as 1 over tan theta. So now let's move on to our next part. For our next problem, we want to solve for sine of 2 theta. And again, it is quite hard to visualize an angle of 2 theta on the unit circle, so trying to solve this in a geometric way will be quite difficult. But instead, we can use this nice trick where we're going to replace 2 theta with just theta plus theta. And you can see here we have the sum of two angles, and so we can use the angle sum identity for sine. So let's do that. We'll get sine of our first angle, sine of theta, times cos of our second angle, which is the same angles, cos of theta, plus cos of our first angle, cos of theta, times sine of our second angle, sine of theta. And notice here that we have a sine times a cos plus a sine times a cos again. So we can replace this with 2 times sine theta times cos theta. And now making a substitution in terms of P and Q, we know that sine theta is going to be our y component on the unit circle. And so this will be Q. So we have 2 times Q times cos of theta, which is going to be our x component, which is going to be P. And so sine of 2 theta is the same as 2 times sine times cos, or 2 times Q times P in terms of P and Q. For our final part, we want to solve for cos of 2 theta. And we can do a similar process as before, where we're going to replace the 2 theta with theta plus theta. And we can use the angle sum identity for cosine now. So we'll have cos of our first angle times cos of our second angle, take sine of our first angle times sine of our second angle. And now we can simplify a bit. So we have cos times cos, which is going to give us cos squared theta. Take sine times sine, which is sine squared theta. Now from here we can go in a couple of directions. Firstly, we can start by just substituting our P and Q values straight into what we have here. And so we know that cos is our x component P, so cos squared will be P squared. And sine is our y component Q, so sine squared will be Q squared. And so we can represent cos of 2 times theta as P squared take Q squared, or cos squared take sine squared. But we can also get our solution in terms of only P or only Q. And we can do this by using our substitutions with the Pythagorean identity, which is cos squared theta plus sine squared theta is equal to 1. So starting with this line here, we can get everything in terms of sine by replacing cos squared using the Pythagorean identity. And so cos squared can be rewritten as 1 take sine squared theta by taking sine squared over to the other side. And then we're left with a negative sine squared theta. And so we got 2 lots of negative sine squareds. So we can get 1 take 2 sine squared theta. And finally, we can make our substitution for sine, and sine is equal to our y component Q. So we get 1 take 2 Q squared. And so our solution for cos of 2 theta can also simplify into 1 take 2 sine theta, sine squared theta, or in terms of Q is 1 take 2Q squared. And now we can do a similar thing to get everything in terms of cosine. So we can replace sine squared with 1 take cos squared by rearranging our Pythagorean identity. And so we get cos squared theta, take, and sine squared can be replaced with 1 take cos squared theta. And by expanding everything out, we get cos squared theta, take 1, take negative cos squared will be plus cos squared theta, and we'll have 2 lots of cos squared, so we have 2 cos squared theta, take 1. which by substituting in our value for cos, we know cos is the x component right off the unit circle, so we have 2p squared take 1. And so cos 2 theta can also simplify into 2 times cos squared take 1, or in terms of p is 2p squared take 1. So that's the end of this example, and now let's move on to our next example. Our next problem is split up into two parts, where the first part requires us to prove a couple of identities, and we have proven the first one, that cos of 2 theta is equal to 2 cos squared theta take 1. We did this in the previous example, so we're not going to prove it here, but we are going to prove the second identity, and that is that sine of theta is actually equal to cos of 90 take theta. And we can do this by using our angle difference identity for cosine and expanding it out, and then hopefully simplifying to eventually get sine of theta. And so let's use our difference identity for cosine. We get cos of our first angle, 90, times cos of our second angle, theta, plus sine of our first angle, sine of 90, times sine of theta, our second angle. And by substituting in our exact values, we know cos of 90 is 0 and sine of 90 is 1. And making these substitutions, we get 0 times cos is 0, plus 1 times sine is just equal to sine of theta. And so we have proven that cos of 90 take theta is equal to sine. Part B gives us some more information that cos of 36 degrees has the exact value of 1 plus the square root of 5 divided by 4. And we have to use the facts that we found in part A, these identities, and our information for the exact value of cos of 36 to prove that sine of 18 degrees is equal to, or has the exact value of, the square root of 5 take 1 over 4. The best place to start is to first find an equation for sine of 18 degrees, because without an equation we will not be able to simplify to eventually find our exact value for sine of 18 degrees. And the way we can do this is by looking at our identity here, that sine of theta equals cos of 90 take theta. So you can see that we have sine of theta here, and if we replace theta with 18 degrees, we will get sine of 18 is equal to cos of 90 take theta, and theta is 18 degrees. And 90 take 18 gives us 72. So we have sine of 18 degrees is equal to cos of 72 by using our identity here. So now we have made some progress where we have an equation for sine of 18 degrees, and now we need to find a way to manipulate this equation in order to eventually get our exact value that we're looking for. And it's probably a good assumption, because we have an equation for cos of some angle, to use our identity here as it is something to do with cos. So what I'm going to do is replace cos of 72 as cos of 2 times 36. And this is because 2 times 36 gives us 72. And the reason why I left it in this form is because it matches our identity here. And so we can expand out into the right hand side, which we will get 2 times cos squared of theta, and we have 2 times theta here and 2 times 36, so theta is going to be 36, and we're just subtracting 1. And so now we've made some more progress where we have expanded our cos of 72 degrees using our identity here. And I hope you can notice that our final piece of information can be subbed into this equation where we have cos of 36, and we can replace this with the exact value that we're given. And so we will get 2 times cos of 36, which is 1 plus the square root of 5 divided by 4. And we had cos of 36 squared, so this exact value is squared, and we're just subtracting 1. And so what we can do is start to simplify this, and hopefully we'll get the result that we're looking for. So let's start by making double brackets. So we'll have 1 plus the square root of 5 over 4 times 1 plus the square root of 5 over 4, because the result is squared. Take 1, and if we multiply these things together, we get 2 times, and we will have 1 plus the square root of 5 times 1 plus the square root of 5, and multiplying the bottom, we get 4 times 4, which is 16. And we're still subtracting 1. And now notice that our 2's can cancel out. So our 2 will cancel out with a 16, and it will become 8 on the bottom of the fraction. And let's use crab claw to expand out the top of our fraction. And we will get, well, 1 times 1 is going to be 1. 1 times the square root of 5 is going to be square root of 5, plus the square root of 5 times 1 gives us another square root of 5. And we have the square root of 5 times the square root of 5, which is going to be the square root of 5 squared, and the square roots cancel out, so we get plus 5. And we're dividing by 8. Subtract 1. And notice here we have a 1 plus 5, so this is going to give us a 6. And we can factor out a 2 on the top to hopefully cancel out with the 8 on the bottom. And so we get 2, the square root of 5 plus 3 divided by 8, take 1. And the 2 and the 8 cancel out. 2 divided by 8 will give us 1 over 4. So there'll be a 4 on the bottom of the fraction. And now notice our final answer is in terms of one fraction. So let's find a way to bring these two values into one fraction. And so we can replace 1 with 4 over 4 to get the same denominator. And now we can just put everything together. So we get the square root of 5 plus 3, take 4, divided by the bottom of our fraction is 4. And the square root of 5 plus 3 take 4, well, 3 take 4 is just going to give us -1. And notice here that we have our final result. Now we have successfully proven that the exact value of sine of 18 degrees is the square root of 5 take 1 divided by 4. And now we can move on to our final example. For our final example, we want to find sine of phi plus 2 theta, given the provided information. And what we can do, because we got the sum of two angles, is use the angle sum identity for sine. So let's do that. That's a good place to start. We will have sine of our first angle, sine of phi, times cos of our second angle, cos of 2 theta, plus cos of our first angle, times sine of our second angle. You can probably notice that there's nothing that we can immediately sub in from our question to the right hand side here. So we're going to have to tackle each section one by one. So let's start with our cos of 2 theta. So let's consider cos of 2 theta. And we know from one of our previous questions that cos of 2 theta is equal to, well, we can choose one of 3 different variations, but because our question has sine of theta given to us, let's get our result in terms of sine, and that will be 1 take 2 sine squared theta. And now we can just sub in our results. So the question gives us that sine of theta is -1/3. So let's sub that in. And this result is squared. And by using our calculator, we get a value of 7/9. Now that we found the value of cos 2 theta, let's consider sine of 2 theta to find the value over here. And so we found from, I think, our first question that sine of 2 theta is equal to 2 times sine of theta times cos of theta. And we know that our question gives us the value of sine of theta equal to -1/3, so we can sub that in. But this time we're unlucky, we have to find the value of cos theta. And we can do that by drawing the unit circle. So we have the unit circle, and the aim here is to find the value of cos theta. And we know that sine theta is equal to -1/3. So let's label that on the unit circle. We know sine is read off the y-axis, and so -1/3 would be a value around here. And because the domain of sine of theta, or the domain of theta for that matter, is between 270 and 360, we're going to only be considering the angle created in the 4th quadrant. So let's write in this angle. And so theta will be what we have here. Now what we can do is consider the right triangle created here. So let's draw a right triangle. And we can label in the sides. So we know that the height of this triangle will be of length 1/3, as we have to go down 1/3 along the y-axis. And we know that the hypotenuse, by definition of the unit circle, will be of length 1, as it is the radius. And what we're trying to find is how far we go along the x-axis. So we're trying to find this length here. We can use the Pythagorean theorem to solve for x. So let's do that. We get x squared plus our height here, 1/3 squared, is equal to 1 squared, our hypotenuse, which is just 1. And solving for x, we'll get 2 solutions. We'll get x is equal to -2 √2/3 and +2 √2/3. And because we're dealing with lengths on a triangle, we can't have a negative length, so we're going to cross out our negative solution and only consider our positive solution for x. And so we have x is equal to 2 √2/3. And now representing this onto the unit circle, we know that this length here is going to be 2 √2/3. And so if you read this value onto the x-axis, the value we get is 2 √2/3. And so that means the x component of the coordinate will be our value for x, which is going to give us cos of theta is equal to 2 √2/3. Now let's substitute our value for cos of theta. So we can replace this with our result. And by solving this on our calculator, we get a value of sine 2 theta to be -4 √2/9. So at the moment, we have found the values for cos of 2 theta and sine of 2 theta. And now we have to find the values of sine of phi and cos of phi to finally complete the problem. So let's leave some room to do this. In order to find sine and cos of phi, we have to use the information that we're given in the question, which is that tan of phi is equal to 4/3. And so let's try visualize this on the unit circle, which I've drawn here. And remember that tan is read off the y-axis. And we have a value equal to 4/3, which is a bit over 1. So let's say over here. And we will extend this out to touch the x equals 1 line. The angle that this point will produce is going to occur in the third quadrant, as our domain for phi is between 180 and 270 as explained in the question. So let's extend a line into this quadrant from this coordinate. And so we'll come down from here. And our angle will be something like this. And so we have phi here. Now breaking this angle into a right triangle and solving for the sides will not work, as we'll have too many variables. So we have to find a different way to get our values for sine and cos of phi. And the way we can do that is still by using a right triangle. And we're going to label the angle in this right triangle as phi. And we know that tan, at the moment, we know that tan of phi is 4/3. And also by our SOHCAHTOA definition, tan is equal to our opposite over our adjacent side. And what we can do now is match up our fractions. So our opposite side will be the top of the fraction, which is 4. So we can mark that in. And our adjacent side will be the bottom of our fraction, 3. And now you can see that we have enough information to find the hypotenuse. So let's use the Pythagorean Theorem. And we get 3 squared plus 4 squared is equal to our hypotenuse squared. And if we solve, we should get h, our hypotenuse, is equal to 5. So let's write that in. And now going back to our SOHCAHTOA definition again, let's find what sine of phi is. Well, that's going to be our opposite over our hypotenuse, and our opposite is 4 divided by our hypotenuse, which is 5. And what about cos of phi? Well, cos of phi is our adjacent side, 3, divided by our hypotenuse, 5. And it would be nice if solving for sine and cos of phi were that simple, but it is not the case here, as we have missed something. And this is because we have to realize that our angle is in the third quadrant of the unit circle, which means we are reading a coordinate of the negative x and negative y axis. And this means that our value for cos of phi and sine of phi will both be negative. And so what we have to do with our solution here is reflect it to the context of our question on the unit circle. And because we have a negative value for cos of phi, we're going to have to make our value negative here. And also our value of the y-axis is read on the negative y-axis. And so our value for sine of phi will also be negative. Now let's rub this out to leave some room to finish off our problem. We have finally found all the components on the right-hand side of our equation. So now what we can do is simply type this in a calculator and see what result we get. And so by typing this on our calculator, we get 4 root 2 divided by 15, subtract 28 over 45 for our value of sine of phi plus 2 theta. That concludes our final example, but before we finish up, I'm going to put a couple of identities on the left here that you can easily prove using the angle sum and difference identities for sine, cos, and tan. Other than that, that's going to conclude this playlist on trigonometric identities.